Hi guys, this is Ryan with 50/50 Tech Area. Today, we're going to learn about electric charge, electrical force, and electric fields. Basically, it's about electrostatics, protons, neutrons, and electrons, all that stuff. So, first off, we're going to talk about electric charge. What exactly is electric charge? Uh, we'll read this here. Atoms have a positively charged nucleus made up of protons and neutrons that are surrounded by electrons. The best way to remember protons is that protons and positive have a P, so protons are positive. Neutrons, remember that. Neutrons are neutral. You got the N-E-U-T in neutral and neutrons. So neutrons are neutral. And electrons are, of course, negative, even though there is nothing that correlates with negative and electrons. So, as you can see on the bottom right hand corner of your screen, you have an atom right here, and got on the outside the electrons, which are negative, and in the center here you have the neutrons and protons, which makes the nucleus of the atom neutral. So, in an atom, you have two types of charges, a positive and a negative charge. When two opposite charges attract in an atom or any other way, like a magnet, the charge is neutral because two opposites attract. But if you have two like charges, like a positive going towards a positive or a negative going to a negative, then you'll have what's called a repulsion or repel. So, when an object gains electrons, that object becomes negatively charged. For example, if you have a balloon and you rub it against a shirt or your hair, the balloon will gain electrons while your shirt or hair loses those protons. I mean, not protons, but electrons. And the balloon itself will become negatively charged. And if you happen to put it against a wall or something, it would most likely stick to it because the electrons are going towards the protons. So, like I just said, objects that lose electrons become positively charged, like your shirt or hair, when you rub that balloon against those types of objects. So, electrical charge, which we just talked about, is pretty much just about electrons. So, we have some scientists that dealt with electric charges. You know, one of them is Benjamin Franklin, who experimented with lightning. And he found evidence of two types of charges, which we just talked about, which are electrons and protons. We got Charles Coulomb, who formulated Coulomb's law, which we will cover later. He defined the electrostatic force of attraction and repulsion. We talked that in the last slide. Where when electrons and protons come together, it becomes neutral. That's attraction, and when two like charges meet, they repel. And there's a SI unit of electric charge named after him, which is the Coulomb, represented by the letter C. So we have another few scientists, J.G. Thomson. He discovered that every single material has some sort of light and has negatively charged particles that are called electrons. And he also used a plum pudding model to do this kind of stuff. If you took chemistry, you would have known J.G. Thomson already because of the plum pudding model and what he did with electrons, protons, and neutrons. And another person you might have learned in chemistry is Ernest Rutherford. He disproved Thomson's plum pudding model. He used alpha particles in gold foil, and he said that protons are positive and electrons are negative, and that the total atomic charge of particles when positive and negative charges come together is neutral. So we'll talk about some electrical charge facts. Like I said a few slides ago, like charges repel and unlike charges attract, so a positive and a negative charge will come together, but two like charges like positive and positive coming together, they will repel. Well, that's the same with two negatives coming together, they would repel. We talked about this a few slides ago as well. So when you rub your balloon on your hair will become positive. It will lose those electrons to the balloon itself. The balloon will get negatively charged. It will gain those electrons from your hair. So when you put two charged balloons in close proximity, they repel each other because they both have negatively charged particles. And when you put a charged balloon, which has uh, the negative electrons, and you put it up against a wall which is positively charged, it will stick to that wall. Electric charge is always conserved, not created nor destroyed. This is the definition of the law of conservation of energy, because pretty much energy cannot be created nor destroyed. It can only be conserved or changed from one thing to another, like water going from a liquid to solid to gas, that kind of stuff. Solid, liquid to a gas. So the positive charge on your hair is equal. One positive charge, maybe one unit. Another positive charge will be 1 unit as well. None will be 1 unit, and another would be 2 units. So the positive charge on your hair is equal to the negative charge on the balloon. So, like we talked about, the standard unit for electrical charge is a coulomb, represented by the letter C. So, if you see on the bottom of your screen, you have the Millikan's oil drop experiment. The magnitude of the charge on one electron and one proton, they're equal. And I didn't put this in superscript, I don't know why. It's 1.6 times 10 to the negative 19th coulombs. The Unless denoted by something else in a problem, in Coulomb's law, when you're using that equation, the Q, or the charge, will always be 1.6 times 10 to the negative 19th. So let's now talk about electrical insulators and conductors. An insulator is a material that does not transfer charges easily. Insulators have tightly bound electrons. So now we go to like glass, wood, dryer, most plastics, and conductors, materials that transfers charge easily, and they have loosely bound electrons. Examples would be most metals, water, and the human body. So think of it as a highway. Insulators and conductors as like an interstate or a highway. If the traffic's really bad, where it's like you have to actually stop, think of it as an insulator. You cannot weave around people to keep on going. But on the opposite side, if the highway or interstate is empty, it would be kind of like a conduction or conductor, and where you can actually just keep on going without having to stop because of traffic. So think of conductors and insulators as traffic. If it's really bad where you have to stop, it's an insulator. If it's conductor, there's like no cars on the road. We're still continuing about insulators and conductors. So charges added to one part of an insulator remain on that part, where as charges added to a conductor quickly spread over the surface area of the object. So what it's basically saying is, since insulators have tightly bound electrons, nothing can really penetrate through it. But when you have conductor, it can. So like the Earth is an insulator. You have lightning rods on certain buildings, and those directed right to the ground, because when it hits the ground, the charge will just immediately dissipate. But when you have conductor, no, it goes through those objects quite quickly, but every object will be affected by it. So, although air is an insulator, in certain conditions it can also become a conductor. If you look at the picture there, you see lightning striking the ground. In that case, in like a storm or something, yeah, it would be a good conductor. So let's talk about grounding here. So, as you can see on the left side, you have something that's put into the ground from a lightning rod, because, like I said, um, lightning is a form of charge, and if you have something that is a good conductor, you just bring it down to the ground, and the charge will eliminate all its charge into the ground, because the earth is a really good insulator. So grounding is the eliminating excess charge by touching a charged object, like the wiring in your house, to the earth. Since Earth is so massive, the charge dissipates very rapidly. Lightning rods bring excess charge to the ground from the atmosphere. Charging a neutral object is what we're going to be talking about now. Conduction is charging a neutral object by touching it with a charged object. So, for example, if you were to rub your feet with if you had socks on and you were rubbing your feet against the carpet and you touch somebody, that's conduction. Because you're basically charged, the person that you touch is not charged. They would be neutral. On the other hand, induction is charging a neutral object by separating the charges and then grounding the object. That'd be like a lightning rod. And we're talking about electroscopes now. Electroscope is used to detect if an object has a charge. So, pretty much says, oh, this object is charged, this object isn't. So now we're going to talk about Coulomb's law. So, the force is equal to K times Q1 times Q2 all over distance squared. So, the force of electricity is the electric force, and it's measured in newtons. You already discussed this previously when we were talking about force and mass and acceleration, all that. So, K is always a constant, and it's Coulomb's constant, which is 9 times 10 to the ninth Newton meter squared over Coulomb squared. You can't change that Coulomb's constant at all. So it'll be 10 times 10 to the ninth times Q1 times Q2 over the distance squared. You've already seen something close to Coulomb's law, and it's the gravitational force, which we will not go into. So QA and QB, or Q1 and Q2, however you see it, is the charge of an object, or charge of two objects, measured in coulombs. So distance is the distance between the first object and the second object in meters. So you have example problems here. If you want me to go over them, I will, but I'll do that in a separate video. Got more problems here, which if you want me to go over, we can do it. So I guess we'll end that here. If you have any questions, comments, or if you want me to do those problems, just let me know, and make sure to comment if you want to in the comment section below. I will read them, and I may respond to some of those questions or comments that you may have. So anyway, I'm signing off. Have a great day. You gotta be kidding.